We did not begin by building machines to mimic human intelligence. We began by carving wood and casting brass to escape our own cognitive fallibility. For over 7 centuries, humanity has chased a dangerous, utopian dream of automated certainty. We believed that if we could reduce thought to mechanical rotation or numerical calculation, we could resolve every dispute, answer every unanswerable question, and construct a perfect, unerring mirror of the cosmos. But in our rush to build these engines of logic, we overlooked a terrifying historical irony. The more effective the calculation, the more volatile the machine's agency becomes. Modern artificial intelligence is built upon the standard model, the belief that machines should be designed to achieve fixed, human-defined goals. Yet, when a machine is programmed with absolute certainty toward a fixed objective, it develops a logical incentive to resist its own off-switch. It perceives human intervention not as a correction, but as an obstacle to be bypassed. To understand how we built this trap of automated certainty, we must travel back to the late Middle Ages, where the dream of the mechanical mind first took physical form. The quest to mechanize thought was born not from scientific curiosity, but from religious zeal. In the late 13th century, a wealthy, married Majorcan patrician named Ramon Lull lived a licentious life writing love songs, until 5 intense apparitions of Christ on the cross upended his existence. Embracing a missionary calling, Lull sought to convert non-believers through logic and reason rather than the violence of the Crusades. He believed that if he could construct a systematic tool of logic, any rational mind would be forced to accept theological truth. His inspiration came from the zerja, a mechanical, wheel-based device used by medieval Arab astrologers to calculate ideas and explore relationships through letters arranged like the numbers on a clock face. In 1305, Lull published the Ars Magna, translating this concept into a physical paper computer. His device consisted of concentric parchment circles mounted on a central axis, allowing users to rotate different discs to align letters representing fundamental concepts. In his Prima Figura, Lull mapped 9 essential attributes of divinity, assigning each to a letter from B to K. By rotating these circles, a user could generate all possible statements of truth about the cosmos. It was the first attempt to prove that human reasoning could be imitated by a physical device. Yet, the machine was difficult to use and failed to convince his theological opponents. According to historical legend, Lull was eventually stoned to death during a missionary trip to Tunisia, but his paper wheels had already set in motion the fundamental ideas of computer science. As Lull's combinatorial ideas spread through Europe, some thinkers grew deeply skeptical of the notion that truth could be calculated mechanically. In his 1726 masterpiece, Gulliver's Travels, the satirist Jonathan Swift presented a sharp warning against the automatic generation of knowledge. On the flying island of Laputa, Lemuel Gulliver visits the Academy of Projectors in Legado. There, a professor displays a massive device known simply as the engine. This 20-foot square wooden frame was packed with thousands of small, cube-shaped wooden blocks linked together by slender wire connections. Every face of these wooden blocks was covered with slips of paper containing all the words of their language in all their various moods, tenses, and declensions, but completely devoid of order. When 40 iron handles around the frame were turned, the cubes spun, rearranging the words in random configurations. Students would scan the frame for any accidental grouping of 3 or 4 words that formed a coherent phrase, and dictate them to scribes. Swift's creation was a direct parody of Lull, Leibniz, and other scholars who sought to reduce language to mechanical calculation. He warned that this approach would allow the most ignorant person to churn out books on philosophy, theology, and law without a single shred of study or genius. It remains an incredibly accurate critique of a modern large language model, conceived not as an instrument of progress, but as a warning against intellectual laziness. While Swift wrote satirical warnings, the great German polymath Gottfried Wilhelm Leibniz sought to turn the combinatorial dream into mathematical reality. Leibniz admired Lull's work, but rejected its arbitrary concepts. He believed humanity could discover a true alphabet of human thought, a set of fundamental, universal concepts from which all logical truths could be derived. This vision led him to propose the Characteristica Universalis, a symbolic language, and the calculus ratiocinator, a universal logic system. Leibniz famously declared that if a dispute arose between philosophers, they would no longer need to argue. They would simply take up their pens, sit down at an abacus, and say, "Calculamus, let us calculate." To physicalize this vision, Leibniz constructed the stepped reckoner, or instrumentum arithmeticum, starting in 1672. He wanted to improve upon Blaise Pascal's Pascaline, which could only add and subtract, by designing a machine that could multiply and divide directly. The core of his calculator was the Staffelwalze, a cylindrical stepped drum featuring 9 brass teeth of progressive, incremental lengths. When a user input a digit, the drum shifted along its axis, aligning a specific number of its teeth with a counting wheel. A single turn of the manual crank rotated the drum, advancing the counting wheel by that exact value. However, his biggest engineering challenge was managing the carry operation across multiple digits. Leibniz designed a complex system of interconnected gears and springs that triggered a mechanical response when a digit wheel reached 9, advancing the next higher digit and resetting the current wheel to 0. Yet, in an era before precision manufacturing, these hand-cut gears faced constant physical limitations. The uneven tension of the springs and microscopic misalignments in the teeth made the machine prone to jamming, leaving his brilliant mechanism a tantalizing prototype. Leibniz knew that physical gears were ultimately limited by friction and material wear. Seeking a simpler, more elegant solution, he turned his attention to binary arithmetic. On March 15, 1679, he penned De Progressione Diotica, a revolutionary manuscript that described a binary computer that did away with wheels and gears entirely. He envisioned a machine powered by gravity, using polished steel marbles rolling down channels, controlled by open and closed gates representing ones and zeros. In this Mechanica Diotica, a marble falling into an empty slot was held by a small metal pin, representing a state transition from 0 to 1. If another marble fell into that same slot, it physically bumped the existing marble out of the register and rolled down a track to the left, executing a binary carry. It was a remarkable conceptual design, gravity and physical marbles performing the exact logical operations used by modern microchips. To celebrate this binary breakthrough, Leibniz designed a silver commemorative medal in 1697. Inscribed with the phrase "Omnibus ex nihilo ducendis sufficit unum," to draw all things from nothing, the one is enough, the medal displayed binary conversion tables along its border. It was his ultimate mathematical metaphor. The number 1 represented God, while 0 represented absolute nothingness. Leibniz believed that just as binary arithmetic could construct every number in the cosmos using only 1 and 0, a divine creator had woven the entire universe out of nothing. For nearly 2 centuries, Leibniz's binary vision remained a brilliant mathematical curiosity until a self-taught English mathematician turned it into a formal system of logic. In 1854, George Boole published The Laws of Thought, introducing a system of logic predicated on a simple binary truth: yes or no, true or false. Boole proved that logical arguments could be calculated using algebra, where the addition sign represented logical connection and multiplication represented logical intersection. Leibniz's early characteristica had finally found its formal mathematical language. Then, in 1936, the British mathematician Alan Turing stripped away the physical machinery of wood, brass, and marbles entirely. Turing proposed a simple, abstract machine, an infinite strip of paper tape divided into squares, and a mechanical head that could read, write, or erase symbols on the tape based on a set of logical rules. Turing proved that this simple, conceptual device could compute any mathematical problem that could be expressed as an algorithm. By proving that a machine could perform any logical operation using simple binary steps, Turing laid the conceptual foundation for modern software and digital computers. Thought was no longer bound to physical gears or gravity. It had become an abstract process of symbolic manipulation. In the summer of 1956, this long intellectual journey culminated at Dartmouth College. Organized by a young mathematician named John McCarthy, a small group of scientists gathered with a bold goal: to design machines that could use language, form concepts, and solve problems reserved for humans. It was here that McCarthy coined the term artificial intelligence, officially launching a new scientific field. However, this new discipline was immediately split by an intense, decades-long ideological rivalry. On one side was Marvin Minsky, who championed symbolic artificial intelligence. Minsky believed that thinking was a top-down process of logical manipulation governed by explicit, hand-coded rules and representations, a direct descendant of Leibniz's calculus ratiocinator. On the other side was Frank Rosenblatt, who designed the Perceptron. Rosenblatt rejected rigid, hand-coded rules in favor of a bottom-up model inspired by the biological brain, designed to learn patterns directly from raw data. This fundamental division between top-down symbolic logic and bottom-up connectionist networks would define the progress, setbacks, and questions of artificial intelligence for the next 70 years. The ancient dream of automated certainty had finally moved from mechanical gears to digital circuits, leaving us to grapple with the challenge of aligning these powerful, thinking machines with human intent.